So here we're going to take a look at what are called partition coefficients or sometimes distribution coefficients. So we'll just write distribution down here, so distribution coefficients. Now a distribution coefficient or a partition coefficient, this is going to be a ratio of two concentrations. So for example, we'll use the symbol D and we'll look at the partitioning of, let's say, uranium as it goes into either zircon or, let's say, an aqueous fluid of some type. So just imagine that we have a cup of water. So in this water here we have a zircon crystal that is floating around down here, and we have a bunch of uranium that is in that water. Well, that zircon can absorb a certain amount of that uranium. In fact, zircon with the composition ZrSiO4, the zircon has a 4 plus charge. Uranium is close enough in size to zirconium 4 plus, especially when it's in the 4 plus state rather than the 6 plus state. So it's really not that hard to make something of the compound uranium SiO4. So uranium will happily substitute in for zircon. So we can ask what would be the distribution of uranium between the zircon and the rest of the fluid. And we could write that as a ratio, concentration of uranium. We don't mean copper. This is U as a subscript for uranium, for uranium and zircon, and then C subscript U for uranium for its concentration in the fluid. And let's say we do some experiments. So how would we figure this out? Well, we do some experiments and we might figure out that when we allow uranium to equilibrate, the zircon and the water to equilibrate with respect to uranium, maybe the zircon has, let's say, 627 parts per million concentration uranium, and the concentration in the fluid is, let's say, 967. These aren't completely arbitrary. These are from a paper by Ayers et al. And so we could take that ratio and we would say that the D value is about 0.68. Now this is a very useful thing to know if we know it from experiments, and we almost always do. That's usually how we figure out these things called D for distribution coefficients. We can do some very interesting calculations. Now we have to maybe be a little bit more specific about how we write this D. We usually write as a subscript that indicates the element that is being partitioned between the two phases. Here the two phases are water and zircon, and then we would indicate the two phases usually with an abbreviation, maybe ZR for zircon and FL for fluid, although ZR is probably not very good because that also indicates the element zirconium. Let's just use Z for zircon. And so we could say this is equal to 0.68. We could do some more experiments, take an average. But what does this mean? Let's say we had a fluid where that fluid crystallizes a zircon of some kind of composition, but now that fluid is gone. Let's say it evaporates. Let's say we're talking about groundwaters, and we found a zircon that was in equilibrium with some groundwater, and the water is gone, and all that we have left is this crystal of zircon. So we have a crystal of zircon here. Let's say we know that it precipitated or equilibrated with some fluids, and the zircon that we find has a concentration of, let's say, 1230 ppm uranium. Well, then what would be the concentration of uranium in the fluid? Well, we cannot analyze that fluid because it's now gone, but we can use the D value. So if the D is equal to 0.68, that would be equal to the ratio of the concentration of uranium in the zircon divided by the concentration of uranium in the fluid. We know this fellow here. We said that it is 1230 ppm. Let's write that again, 1230. So we have 1230 divided by concentration of the fluid in concentration of uranium in the fluid is all equal to 0.68. So that means that the concentration of uranium in the fluid, again, don't mistake that for copper, that's a C with a subscript U, is equal to 1230 divided by 0.68. Let's carry out the units. That's units of ppm. There is no units on the D because the ppms cancel out. So we have ppm of 1230 divided by 0.68, and that gets us a value of 1808.8 ppm. So that is the concentration of uranium in the fluid. That's a very powerful thing to know. It means we can use crystals as a record of what might be in a magma or a fluid or some other kind of phase, so long as we know that this thing, this crystal that we are analyzing, was in equilibrium with the phase that we are interested in.